We often give routers all the credit for moving data across the internet, but routers specialize in connecting distinct networks across the globe. When it comes to the heavy lifting inside a single office or home, moving data between computers on the same floor, the job falls to the switch. This OSI model recap slide shows us exactly where these devices live. Layer 2, the data link layer. Because they operate here, switches don't look at IP addresses. Instead, they make every forwarding decision based on physical hardware IDs called MAC addresses. This creates an immediate hurdle. When you take a brand new switch out of the box and plug in 3 computers, its internal memory is a total void. The switch has no idea which computer is plugged into which port. To deliver data without crashing the network, it has to build a functional directory of its surroundings from scratch, starting with an absolute blank slate. To give the switch the information it needs, the sending computer wraps its raw data packet inside an outer layer of metadata. Looking at this diagram, we see this 26-byte outer shell, the Ethernet frame. The first 8 bytes are the preamble and the start frame delimiter. These act as a synchronization signal, a digital drumbeat that wakes up the receiving network card and announces that a real message is beginning. Immediately following that is the source MAC field. This contains the globally unique 48-bit hexadecimal identifier of the specific computer that sent the data. Next is the destination MAC field, which holds the target ID of the computer meant to receive the message. These specific header fields provide the exact raw data the switch needs to categorize its environment. By reading them, it begins to map its physical universe. Let's track the logic. PC1 sends a frame intended for PC2. That frame travels down the cable and hits port 1 on our empty switch. On this diagram, we see the switch's first step. It reads the source MAC of the incoming frame, recording PC1's MAC against port 1 in its address table. The switch has officially learned where PC1 lives. For its second step, the switch reads the destination MAC to see where to send the data. But because the table is still empty for PC2, it finds no match. This is an unknown unicast, which triggers a failsafe. The switch duplicates the frame and blasts it out of every single port except the one it arrived on. Flooding ensures the frame reaches the intended target. However, relying on this constantly would drown a busy network in digital noise. To operate efficiently, the switch needs to finish its map. The flooded frames reach every machine. The wrong computers see the mismatch and drop the data, but PC2 recognizes its own address and sends a reply back to PC1. Now, look at the updated table in this diagram. When the reply hits port 2, the switch reads the source MAC, recording PC2's location. Finally, it reads the destination MAC, addressed to PC1, and checks its table. Because PC1 was mapped to port 1 during the very first exchange, the switch recognizes this as a known unicast. Instead of flooding the entire LAN, the switch directly forwards the frame down port 1 exclusively. This strict adherence to the binary rule, learn from the source, deliver by the destination, transforms a chaotic hub of cables into a precision delivery instrument. But network environments change. Imagine an employee unplugs their laptop from port 1 and moves to a conference room on port 3. If the MAC table was permanent, the switch would continue firing PC1's data into an empty port, creating a black hole for that information. This slide shows the solution: dynamic aging. Learned MAC entries get a 5-minute countdown clock. If a device goes silent for 300 seconds, the entry is wiped. But if it sends a frame, the clock resets, keeping the table accurate. The network switch functions as a living algorithm, constantly building, pruning, and perfecting an invisible map of our hardware, keeping the digital world flowing flawlessly.